Okay. Do I have the right one?
Yeah.
Radio wave characteristics. Let's see. This will, and I shouldn't have mentioned it on those others of how many exam questions that represented. In this set, there's three groups, A, B, and C, so there's three exam questions out of it. So we have electromagnetic. A radio wave is an electromagnetic wave. Okay, it's the same as light. Light is an electromagnetic wave. Consists of an electric field and a magnetic field that vary in intensity. They're orthogonal, means they're 90 degrees apart. And if you see the blue field there is the magnetic field, in this case going up and down vertically. The orange, red, whatever you want to call that, is horizontal. That's the electrostatic field or electric field. So any radio wave, light wave, X-ray, anything in the spectrum is going to be composed of both an electric and a magnetic field that are orthogonal to one another. And the propagation direction is going to be what we call broadside to the antenna element. In this case, we'd have your antenna that way. Okay, you're going to propagate a wave perpendicular to that. It's actually going to be spherical until other things affect it, like the ground, be a big toroid. The main thing is to remember that the electric and the magnetic fields are at right angles, and that there is an electric and a magnetic field. So what are the two components of a radio wave?
Electric and magnetic fields.
What is the relationship between the electric and magnetic fields?
They are at right angles.
Okay. Now, we also need to talk about frequency and wavelength in the overall electromagnetic spectrum. We measure frequency as the number of complete cycles per second, and we use hertz to represent it, named after, I think it's Heinrich Hertz. We measure the wavelength, which is how far a wave travels in one cycle. And we know that for all practical purposes, a radio wave, just like a light wave, is going to travel at the speed of light or very close to it. So it makes it easy to calculate what the wavelength is if we know the frequency, because we know the speed, which is 300 million meters per second. We use the Greek symbol lambda, which is that funny looking thing, to represent wavelength. So you will see a lot of times a lambda over 2 or a lambda over 4 representing a quarter or half wavelength. In antennas, in most cases, there'll be a half wavelength long with quarter wave elements. Exception being a quarter wave vertical, but it has a virtual quarter wave into the ground. And I mentioned the speed of light is approximately 300 million meters per second. It's actually 299.9 something. It's very close to 300 million. Now, that is in a vacuum in free space. when a wave travels through a conductor, it's going to be slower. It has what we call a velocity factor, which is dependent upon the dielectric around the conductor, which affects the capacitance. There's distributed capacitance along it. And in some cases, it could be as slow as like 0.66 times the speed of light. So when you figure like in antennas or in coax, you need to know what that velocity factor is, because the electrical length will not be the same as the physical length. Physically, it will be shorter because the wave travels slower. This is showing the spectrum where we're going from, I'm not sure why they chose to do this in kind of backwards, but the increasing wavelength is a slower or lower frequency. Normally you think of it going the opposite direction, but so here we have 100-meter wavelength, which is down. What's the low end of the HF band? 160?
Yeah, 160 is the lowest.
So somewhere around the end of this chart would be the bottom of the high frequency radio, amateur radio band, 160 meters. As we go up in frequency, and you can see that, well, let's see. The VHF normal handy talkie 2-meter band is going to be right about here. The 70 centimeter band is somewhere over here. And we get up to like a gigahertz. So the entire amateur radio band is going to be in this area. And that's what we call radio waves. When we get up to shorter wavelengths, then we get into infrared light. Then we actually get the light spectrum, which is pretty narrow. And then we get into ultraviolet and X-rays and gamma rays, and I don't know what's beyond that. The one thing here, and we'll get to it later, when we get to ultraviolet and above, this is called ionizing radiation, where below it's non-ionizing. And what that means is there's enough energy, and you can see the increasing energy, to actually disrupt cells. So if you notice, if you got a sunburn from ultraviolet, if you got a severe sunburn, you can do permanent damage to your skin. Can wipe out your eyes. As you go higher and higher in frequency, and you know the things that too much X-rays can do.
Turn to the Hulk.
And then gamma rays, that's the Hulk, right?
Yeah. That's right.
No telling what those do. But those things can actually change your DNA and stuff in your cells and disrupt them, cause permanent damage.
Like nuclear radiation.
Yes, which is gamma rays and X-rays. And the reason I bring that up is part of the safety stuff we'll discuss is radiation exposure, where exposure to radio waves causes heating, okay? But you can have enough heating to cook your eyeballs once. It's like cooking an egg and they turn white. So that's a danger. That's why it's covered in the safety thing. And you have to actually look at the amount of radiation exposure you're getting. So you need to stay a certain distance away from high power antennas and things like that. Even a handy talkie at 5 watts, you should be 10 inches away.
Right up to your face.
Well, you can do it for short periods of time, but the average exposure, you better not be closer than 10 inches for long periods of time. Now, you're not much over the exposure, and it's, I'm sure it's got a safety factor of several times, but
Which is probably why they have a limit on how many watts they can transmit.
yeah, it's part of the reason. And where you point it. And it's also different when you're pointing it at your neighbor versus yourself, because that's got uncontrolled. They don't know they're being exposed, where you do. So the exposure level is half that you're allowed to point at your neighbor. So when you get your 1500 watt transmitter connected to your 15 element Yagi and you point it next door, you're not supposed to do that. Okay, so calculating wavelength. We know the speed of light. So, and wavelength is how far the wave travels. We know how fast it's going. So if we know the frequency, then, which is how many times per second it changes, then we simply divide the speed of light by the frequency and get the wavelength. It's kind of like the Ohm's law formula. You can get frequency or you can get wavelength if you know the other one, because you already know the speed of light. So if I want the frequency, I divide 300 by the wavelength. Now, the reason we're using 300 is because we're using it in megahertz. So we know that the speed of light is 300 million, or 300 times 10 to the 6 meters per second. And a megahertz is so many times 10 to the 6 hertz. So I can cancel out the 10 to the 6 and just use 300, which simplifies the calculation, unless you just like to deal with a lot of zeros. And then you can do it in hertz, in meters. So the lower the frequency, the longer the wavelength, and the shorter the wavelength, the higher the frequency, which was on that other chart. And these are actually questions about that. Here's some formulas for examples for the 40 meter band, which kind of the middle of the band is like 7.15 megahertz. So that's 41.95 meters. And we call the amateur radio band, we divide up into meter bands. So these are approximate. I mean, they never come out exactly like the 20 meter band is actually below 15 megahertz. They're going to be in the 14 megahertz range, but we call it the 20 meter band because it's close and even numbers. So what is the velocity of a radio wave traveling through free space?
Speed of light.
Which is how much? How many meters per second?
300 million.
Good.
Yeah.
What is the approximate velocity of a radio wave in free space? The velocity of a radio wave in free space. Speed and velocity, in this case, are the same.
300 million
Bravo.
meters per second.
Bravo.
Let's try Bravo. What is the formula for converting frequency to approximate wavelength in meters?
The speed of light it's D. No, not D. The speed
Yeah.
of light divided by the frequency.
300 divided by the frequency.
Yeah. And yeah.
Delta. Let's try delta. Very good. Yeah, these ones where they write out the equation are confusing. You have to read it carefully.
The key on these questions like this is to be sure you know what the multiplier is. So in this case, you're looking at megahertz and meters rather than hertz.
Right. What is the relationship between wavelength and frequency?
The wavelength gets shorter as the frequency increases.
Right. And if you look at the formula, you can see that. Because as F gets bigger, lambda's got to get smaller. Okay, so we refer to radio frequency as essentially any alternating current signal. I mean, technically, a 60 hertz AC in your wall socket could be radio frequency, even though it doesn't radiate much. There's not enough energy there. Because remember, energy increases with the frequency. So it's very low energy as far as RF, the wave. And we talked about using the approximate wavelength to identify the amateur bands. 2 meter band is 144 to 148 megahertz. So as a technician, you can operate in the 2 meter band and also the 70 centimeter band, which is 430 to 460, I think, or at least 450.
Boy,
Yeah, and the amateur band is 430 to 450. And above that is GORS.
And we group the amateur radio bands. Well, I guess not just amateur radio, all of them, in what we call medium frequency, high frequency, very high frequency, and ultra high frequency. There's actually some others. There's a low frequency, which not many people operate in. And I think there's a super ultra high or something like that. But most amateur radio is going to be in the MF through UHF bands. And the medium frequency, which may be on the next chart. Well, this is a copy of the technician bands of where you're allowed to operate with a technician license, what modes and what power. And I have some copies of these, I think, if you'll.
are those popular? The 23 and 33 centimeter?
I would say no.
I don't see any radios that you could buy.
Oh yeah,
that,
my 9700 does.
I've only been in, doing this for a couple of weeks, but I do a lot of internet searches when I'm bored. And I look at radios and what they do and compare them.
There are questions on the extra exam if you go that high about 23 and 33 because they're used for specific things. But I'm like you, I haven't seen many radios at all that have them.
Yeah.
Yeah, because we're just talking about the danger putting this up to your face. We're operates at about a 900 megahertz.
900.
Right.
And so.
But it's not
it only
5 watts
works in
either.
Milliwatts.
Yeah.
It only works in milliwatts because it's dangerous. I put it up to my face for an hour.
Right.
It's in milliwatts to keep it from cooking my eyeballs, like you said. But the radio, if a walkie-talkie or whatever is working in watts, you can hurt yourself at those frequencies.
Right.
So
But-
they must be they must be operating in milliwatts. Guessing.
Well, it's hard to get a lot of power at those frequencies. So I think my radio might do 20 watts up there. I forgot whether it's 33
far
or
away from you.
Well, yeah, I mean, antenna's up on the roof.
Well, you're safe distance from.
Oh, yeah, yeah.
Because it's like standing in front of a cell tower, and that's a lot less. Well, the 33 centimeters is staying in the cell tower, but the 1240, that seems really dangerous to me.
I don't think you're gonna find a handy talkie that does 23 or 33. Now, there are some tri-bands, like the new Kenwood is one. And I think it's what, the 220? Huh?
Have you seen the price tag?
No, I suspect not cheap.
Yeah, it's out of my range, sir. Yeah, and the thing is, the 1.25 meter band. Other countries don't have that, so it's hard to find radios or antennas, either one, to function on that band.
And my scanner doesn't even do it, so I'm
Yeah.
kind of disappointed. I can't hear anything there.
We need to start using it. Say that. I think there's one 220 repeater in the area. Well, I don't actually.
I think there might be more than one, but usually that band is used for like control of the repeater.
Yeah.
It's like a control band where you can go do maintenance and things on the repeater, shut it down, reboot it, things like
I'm
that.
sending remote commands instead of going over it.
This is what I was just looking at on the internet.
Yeah,
You ask if 160 meters is the low end of the HF, but according to that, it's at the high end of the MF.
yeah. So-
1.8.
What does the title say? This one's blocked out.
Oh, this is the electromagnetic spectrum, and this is just showing the bands. The medium frequency goes, and these are numbers you need to remember. 300 kilohertz to 3 megahertz. Your HF band, which is where most of the amateur activity is going to be, is 3 megahertz to 30 megahertz.
That's what they do. I'm assuming these are new terms to me, but QRP is what I hear a lot.
QRP has power, reduced
Right, but
power.
they're usually down in those low bands. And they're talking to people really far away.
Yeah.
Doing in the
Well, that has to
7
do with
megahertz,
the reason
14 megahertz.
where they are, it has to do with propagation. Okay. To get somebody really far away, you've got to be in the right sunspot cycle, you've got the right time of day, the right elevation angle, because you've got to refract your signal through the ionosphere with multiple bounces to get halfway around the world.
But it looks like fun.
Oh, yeah, it is. And some days it works and some days it doesn't. It's not very predictable. Okay, so HF is 30, there's 3 megahertz to 30 megahertz. 30 megahertz is 10 meters. VHF is where you get 6 meters up to the 2 meter band. I guess 1.25 is still there, right? I've never used that. I don't have a radio that does it.
1.25 is the 220 band.
And then UHF is 300 megahertz to 3000 megahertz. So you see these are going up by 10.
Yeah.
That's the multiplier in each of those ranges, which is the thing to remember. So this is your 70 centimeter band and on up. In addition to frequency, which of the following is used to identify amateur radio bands? approximate wavelength. And I just listed most of the bands available to US amateurs. If you're an extra, you can do all of these and all modes. So what frequency range is referred to as HF, or high frequency?
C.
B.
Charlie.
C, sorry.
That's okay. You'll remember it now.
Yes, I will.
3 to 30. What frequency range is referred to as VHF?
B.
Oh, yeah, right. Bravo.
Remember, HF, what follows? VHF, right?
3 to 30, yeah, B.
Yeah.
B is in boy.
What frequency is referred to as UHF?
C.
Delta.
Good. What does the abbreviation RF mean?
Alpha. Alpha.
So we learned that radio waves consist of electric and magnetic fields. The electric and magnetic fields are orthogonal or perpendicular to one another. The speed of light is 300 million meters per second. We do wavelength in meters, and it's 300 divided by the frequency in megahertz. Wavelength decreases as frequency increases, and it increases as frequency decreases. We represent the amateur radio bands in the HF, VHF, and UHF, and those frequencies, which, as you saw, are test questions. And then RF refers to any frequency.